All right, this is the singular value decomposition video 2. So what we'll do in this video is we'll talk through how to come up with the u and the sigma and the v. So in other words, given an m by n matrix A, how can we obtain u, sigma, and v such that A is u sigma v transpose, along with u and sigma and v having the properties that we said that they needed to have in the first video, right? Orthogonal for u and v and diagonal for sigma. So what we'll do is we'll step through the process. And the process requires, there's some sort of serious linear algebra that's used, some simple calculations that are used. Most of that I'm going to omit, right? The simple calculations are in the textbook. The long calculations are results of linear algebra that we omit from this course. But really, I just want to get to the heart of the process. So I'll point out when those things come up and how hard they are, but I won't go into detail in them. So, step 1. I want to consider two matrices. So the matrix A transpose, right? So this matrix A, this is M by N. So it turns out that A transpose will be M by M. And A transpose A is N by N. Now, that's easy to show. Now, what I'm about to say next is hard to show. So it turns out that by the spectral theorem, this is probably the biggest first huge theorem in linear algebra. This tells us that A transpose, this will have m eigenvalues up to multiplicity and m perpendicular eigenvectors. Has m eigenvalues up to multiplicity and has m perpendicular eigenvectors. And it also follows, same theorem, that A transpose A has n eigenvalues up to multiplicity and n perpendicular eigenvectors. So, just for reference, these facts are easy. These facts are hard. Now, there's a couple of easy things. Is that the eigenvalues, the non-zero eigenvalues, actually, so let me say it this way around. All of these eigenvalues will be greater than or equal to 0. And the ones that are greater than 0 are shared between these two matrices. So by shared, what we mean is, for example, if A transpose has an eigenvalue of 3, then so does A transpose A. If A transpose has an eigenvalue of 2.7, then so does A transpose A. Now, A transpose may have an eigenvalue of 0, and A transpose A may not. So they may not share 0. But neither of them has an eigenvalue of, say, negative 10. So this fact, these two facts, if you like, these are easy to show too. Those are in the text. You're welcome to look or ask me. So what we're going to do is we're going to take the ones that are shared. Because they're positive, we're going to take the square roots and call those square roots sigma. Right? So take the positive ones, take the square roots, call them sigma I. So thus the eigenvalues, or the, if you like, the shared positive eigenvalues, those will be sigma 1 squared, sigma 2 squared, up to sigma k squared. Now, if you're wondering what the k is in this case, K is the minimum of m and n. So the key point here is, of course, that since they're sharing eigenvalues, right? If this guy has, let's say, if A transpose has m of them, and A transpose A has n of them, then sort of together they will have the minimum of those, and the remainder will be 0. So together, the non-zero shared will be the minimum. Right, the rest will be 0. And we'll see that come up with an example, or rather in our examples. So then step 2 is we do the following, right? For each of these sigmas we do something. Or we'll say for each eigenvalue sigma I squared, because remember the sigma I squares are the eigenvalues, we find two things. We find ui, which is a unit eigenvector in Rm of AA transpose. And we find Vi, which is a unit eigenvector in Rn of A transpose A. Now, we have to choose these to satisfy the following requirements, that A transpose Ui equals sigma I Vi, and A Vi equals sigma I Ui. Now, in practice, this pretty much always happens. The only time that we actually need to make choices is when we have multi-dimensional eigenspaces and there are some complications. But this is almost always something we can overlook. Basically in most applications. And to be fair, when we do these in applications, we're doing these in software. So we're not actually going to be doing these by hand anyway. So then step 3 is we construct our matrices as follows. So we let the diagonal entries in sigma be the sigma I. So these are usually, let's be clear, in non-increasing order. You can think decreasing order if you like, as long as you're comfortable saying that if you have the same eigenvalue twice, that you just list one after the other. But if you want to be formal, you say non-increasing. That way, you know, the biggest one goes first, and then so on and so forth. So then what we do is we let sigma be the ui in the order corresponding to the sigma I, and then we let the vi, this is the u, not the sigma. We let v equal the vi in the order corresponding to the sigma I. Now, it could be that when we're done, that either, well, it almost always will be that when we're done, that u and v are not full, in which case we can fill them up with any perpendicular unit eigenvectors. And we can typically do that using the eigenvectors that remain that correspond to 0. So fill either u or v. One of them, you know, only one of them it'll turn out will need to be filled, but fill these with the remaining eigenvectors corresponding to 0. And frankly, what we mean by that we'll see as we go through an example. We'll go through a couple of examples. So again, this seems fairly complicated. So what I'll do is I'll clear the screen, and then we'll go through an example. We'll go through the one we saw at the end of the first video, so you see where all these numbers were coming from. And then we'll do another one. And we can talk about all these little details about checking things and perpendicularity and so on and so forth as we go. So So here's some examples. So let's go back to this A. This is the A we had at the very end of the first video. 1, 0, 2, 1, 0, negative 1. So what we'll have here, this is 2 by 2. So U will be, sorry, this is 2 by 3. So U will be 2 by 2, sigma will be 2 by 3, and V will be 3 by 3. So what we first do is we write down A transpose, and A transpose A. So A transpose. This is the matrix 5, 2, 2, 2. And A transpose A. This is a 3 by 3 matrix, 1, 2, 0, 2, 5, negative 1, 0, negative 1, 1. Now, if we find the eigenvalues for this, this first one has eigenvalues 6 and 0, 6 and 1. The second one has eigenvalues 6, 1, and 0. Notice that the positive ones are shared, but the second one has an extra 1, and that 1 is 0. So this immediately tells us sigma. Right, what we do is we take the square roots of those, right? So these two together tell us that sigma 1 squared is 6 and sigma 2 squared is 1. So this tells us that sigma 1 is the square root of 6, sigma 2 is the square root of 1, which is 1. So those are the values. These are actually called the singular values. That's where the name comes from. Those go into the diagonal entries of sigma. And then since it's got to be 2 by 3, it fills in with zeros. So the square root of 6 and the 1, those are the key things here. So next, we take our two eigenvalues. So the first eigenvalue is sigma 1 squared, which is 6. So we find a unit eigenvector of A transpose. Call that U1. That is going to be negative 0.89. I'm going to write this, when we did this before, we did it to 4 decimal digits. I'm just going to save us some space and sanity. Do it to 2. Really, they go on forever. They're just approximate. So, and then we also find a unit eigenvector of A transpose A. Call that V1. That'll be negative 0.37, negative 0.91, and 0.18. Now, in this case, I won't show the calculation, but everything works nice. There's no dimension issues. So here, it turns out that A transpose U1 equals sigma 1 V1, and A V1 equals sigma 1 U1. Again, like I said, this is not something we overly worry about. In rare cases, choices would need to be made, but for us, not so much. So then what we do is we go on to the second sigma. So sigma 2 squared is 1. So we look for a unit eigenvector of A transpose. We get U2, 0.45, negative 0.89, and we look for a unit eigenvector A transpose A. This will be our V2. This is negative 0.450 and negative 0.89. And here again, A transpose U2, this can be checked, is sigma 2 V2 and AV2 is sigma 2 U2. Now then, we're almost done. So far, this is what we have. Right? The original starting matrix. There'll be one last step involved, but it's pretty simple. But I want to make sure that we see why it has to happen. So the first thing we do is we take the columns in U. All right, U is 2 by 2. We have two columns. That's U1. This was our U2. Notice those are perpendicular. If you dot them, you will get 0. So U is great. Then we take our sigma. That's great. Then we go to construct our V, and we start putting together the columns in V, which needs to be 3 by 3. And we notice we don't know what goes here. Right, what goes, like we don't have something for this last column, and it has to be 3 by 3. So then we go, well, wait, hold on. The ATA was special, right? If we look back right here. Now the reason we're looking at ATA is that the V's are coming from ATA, right? Like the first V1 came from ATA, the second V1 came from ATA, well the V2 rather, the second V came from ATA. So we go back to ATA right here, and we find an eigenvector for that. Turns out a unit eigenvector for that is 0.82, negative 0.41, negative 0.41. So what we do is we insert that into the matrix. Oops, there should be a 2 right there. Also, this should be a transpose right there. Just a bad habit of mine to forget to write that. So now we can fill this in. We have our U, we have our sigma. And we have our, finally, we can fill this in. Our V transpose. So that's our U. And again, don't worry right now about why these are actually relevant. Like it's not relevant right now why they're relevant. It'll be relevant soon when we start to look at what we're actually getting here. So let me clear the screen. I'll go through one more, but the process will be the same, right? Picking out the eigenvectors, picking out the eigenvalues, seeing that they're common, seeing that they're shared, etc. So we'll say given A in this case, we'll sort of do slightly different dimensions so we see how things work out this way around. So we'll start with a matrix which is 4 by 2. Like this. Right? So this is 4 by 2. So our U will be 4 by 4, sigma will be 4 by 2, and V will be 2 by 2. So same exact process. We find A transpose. This is 4 by 4. This is pretty icky. This is 10, 6, 4, 5, 6, 4, 2, 4, 4, 2, 2, 1, 5, 4, 1, 5. We find A transpose A. This is much nicer. This is 2 by 2. Notice that these are always symmetric. That's easy to prove, and that's actually the reason we get all the nice stuff about them. Now the eigenvalues for this first one. So we have the, I'm going to approximate these. This is 18.26. I'll just do 2 decimal digits. In the text I did 4. This is to save us some grief. So this has 3. Even though it's 4 by 4, the last one has some multiplicity, right? So if we wanted to be really, really honest, this is what we would write. This is multiplicity 2. It's a 2-dimensional eigenspace. This has the same 2 non-zero ones. So we can therefore say the following. We can say that sigma 1 squared will be 18.26. Sigma 2 squared would be 2.74. The singular values of the square roots of those are sigma 1, this is the square root of 18.26. This is 4.27. Again, approximating. The square root of 2.74 is 1.65. So this tells us sigma. And sigma, keep in mind, is 4 by 2. So those values go on the diagonal. And then we fill it in with zeros. We fill it in down because it's 4 by 2, because of the size. Then we go through the next process. We look at eigenvectors of that first sigma 1 squared. So from, or unit eigenvectors, let's be clear. From AA transpose, we get the first one. This is negative 0.673. Again, I'm going to round these from the book. And from A transpose A, we get our V1. This is much nicer because it's two-dimensional. This again satisfies, or these again satisfy the two requirements that we had. A transpose U1 equals sigma 1 V1. A transpose, or A V1 equals sigma 1 U1. Again, not something we worry overly much about, except in really weird circumstances. And then we look at the unit eigenvectors. Actually, let me do this. I want to make sure we have space to write the final matrix calculation. So then we look at the unit eigenvectors of this eigenvalue, the second one, 2.74. We find from A transpose, we have our U2. Again, this is the icky one. This is 0.36, negative 0.16, 0.52, negative 0.76. And from A transpose A, we have V2, which is not so bad, 0.99, negative 0.13. Again, these approximations just to keep us sane. And again, in this case, A transpose U2 equals sigma 2 V2, A V2 equals sigma 2 U2. That can be checked. So now in this case, let's just, before we try and write down the final result, what we'll notice here is preemptively is that for the U vector, right, U is 4 by 4. Right, we notice that up here. U is 4 by 4, but we've only got two vectors. So this immediately tells us we need to fill in. We need two more vectors for U. So if we go back to AA transpose, right, so back here, that had the extra two zeros. The fact that it was multiplicity 2 means that you can find two vectors that span the two-dimensional eigenspace. So use the eigenvalue 0 from AA transpose. This will give us two more eigenvectors. There are a couple different choices here, but we'll use, I'm just using what MATLAB gave me when I did this. This should be a 0.80 and 0.27. So these two sort of will fill in the rest. So now that we have all of these, we can fill in the final result. Let me pick a different color so it's all clear and separated. Let's do blue. So the final result is that our original A so this is a really icky one. This is the U. So we're going to put all our U's together. That's our U1. We have our U2. And we have our miscellaneous things that we just put in. Now notice that it doesn't matter, it turns out, which order I put these in. Like I could switch the order of the last two. Then I put in the sigma. And then we put in finally the V. And that gets a T. So this is our U, our sigma, and our V transpose. And again, a couple interesting notes. One is that the order, I'll do these in red. This is not something we need to worry about overly much, but it's worth keeping in mind for those that are sort of really keeping a keen eye on things, is the order of these two doesn't matter, right? And what's even actually interesting is they don't even really matter to the product at all. Because, for example, when you do the multiplication of the first two, right? This is, so the SVD is done, but I'm just going to point this out in closing. When you multiply these two together and you do row times column, the zeros here mean that these values don't actually matter, right? Like it really actually doesn't matter what you stick in there, as long as you have two vectors which are unit vectors and which are perpendicular to each other and to everything else, right? So taking them from the eigenvalues and the eigenvectors is just a handy way to pick it. But in reality, you could stick anything you want in there and the product would still work. It wouldn't technically be an SVD, but the product would still work out. So now we know the process to calculating these. It still hasn't told us what they're good for, but I just want to point out the important things here. Let me erase some of the pink. I just want you to notice the really important points here. So the important points to keep in mind in closing, I won't overwrite too much, is that these guys are perpendicular, they're unit, they're perpendicular to one another, and that these entries are in non-increasing order, traditionally. It will turn out for us that the things in V we won't actually need. What happens with singular value decomposition is you get to make a choice between which matrix you care about, depending on the way that you're structuring your application. So for us and for most people, it's the U and the sigma that are the critical ones. So the V sort of falls by the wayside. But big things to consider. The U's are all unit vectors, are all perpendicular, and the sigmas are in decreasing order. All of that is going to be really, really essential as we go forward. So let me call that done.